This minute physics video will focus on the forces unit, and particularly Newton's laws as applied to the high bar back squat. We will calculate force using the given values of the mass of the squatter, the mass of the barbell, the acceleration of gravity constant on Earth, and the difference between the final and initial velocity and that of time. When calculating force exerted on and by the lifter, we must consider the forces acting on the person. There is a downward pull of gravity on the person squatting, and they are also exerting a force by pushing directly against gravity in order to stand back up. The lifter must also exert a force to stop herself from continuing towards the floor. We will neglect any air resistance for this scenario. Note that the calculations are not 100% accurate, since we cannot tell with the given equipment and information how much force is coming from each muscle activated during the squat. An object's mass is defined as the acceleration of gravity multiplied by the system's mass. The acceleration of gravity constant was found using Newton's 3 laws of motion, which directly apply to the movement of the squat. There is zero acceleration at the top and bottom of the squat. The lifter must apply equal or more force to prevent themselves from being crushed by the weight bared upon their shoulders. The greater the force acting on the squatter, the greater their acceleration. The greater mass upon the lifter will cause acceleration to decrease. The gravitational force pulling the squatter downwards is equal to the normal force they must exert to stand back up. In this situation, we will analyze the high bar back squat, both squatting down with the bar and ascending back out of the hole. To calculate the force of the athlete pushing through the floor, also called the normal force, we will find the sum of the acceleration multiplied by the mass of the athlete and the mass of the barbell. From the calculations, we can conclude that the squatter does not accelerate at the bottom, and therefore the acceleration equals 0 and the net force equals 0. The lifter must exert a force equal and opposite to the force applied in order to stand back up. We refer to this force as the normal force. Since the downward force exerted on the lifter is 1,313.98 newtons, they must exert the same force, if not more, in order to get out of the hole and stand back in the initial position.